Chapter 7, Section 4, Application of Inverse Matrix to Linear Regression. In this section, we will see how matrices and inverse matrices can be applied to multiple regression analysis. In the previous video, I explained that the multiple regression equation is expressed in this form, and that the product of the transpose matrix of X and the original matrix X provides information on the correlation between independent variables. It is important to check the problem of multicollinearity. However, the purpose of multiple regression analysis is to examine the relationship between the independent variable and dependent variables. Up to now, we have investigated the underlined part only. The remaining parts contain the inverse matrix and transpose matrix. They provide us with information on the relationship between the independent and dependent variables. Understanding the role of these inverse and transpose matrices provides a deeper understanding of why matrices play an important role in multiple linear regression. Generally, we can express a multiple regression model by this equation. As we saw before, we can express this multiple regression model by matrices and vectors in this way. The vector y on the left side is the observed value of the dependent variable. X is the vector of independent variables, and beta is the vector of regression coefficients. The product of x and beta is the vector of predicted values. And epsilon is a vector representing the error between the predicted values and observed values. The parameter we want to optimize in multiple regression analysis is the regression coefficient. To do so, multiple regression analysis seeks to find regression coefficients that minimizes the sum of squared errors. Let S beta be the sum of squared errors. The sum of squared error is a function that uses the regression coefficient beta as an input value. As the value of the regression coefficient is changed, the sum of squared errors will also change. The regression coefficient that minimizes the sum of squared errors is the optimal regression coefficient. The sum of squared errors can be expressed as the product of the transpose of the error vector, epsilon, and the original error vector, epsilon. Let's check this with a simple error vector. Since the error vector is a 3 by 1 matrix, the transpose error vector is a 1 by 3 matrix. Substitute this into the expression of the sum of squared error. Calculating this, we can confirm that it is the sum of squared errors. Now, let's solve the problem of minimizing the sum of squared errors. Once again, let's go back to the multiple regression equation expressed using vectors and matrices. By subtracting x beta from both sides, we can express the error vector epsilon in this equation. Substitute this in the right side of the function of the sum of squares of the errors. Expand this. This looks complex, but by differentiating this equation with respect to beta, we can find beta that minimizes the sum of squared errors. Differentiate this equation with respect to beta to find a condition that minimizes the error. Let's decompose the equation. Let's focus on the first term. Since this term does not include beta, it can be regarded as a constant term. Therefore, differentiating the first term results in 0. Now, let's look at the second term. Here, we need to use the product rule for the derivative of the dot product of vectors. It is complex, so here, you can just think that this formula holds in this way. if we apply the formula, A in the formula corresponds to y, and B corresponds to x beta. Using the formula, we can differentiate the second term in this way. The third term can also be differentiated by the derivative law of inner product. The third term can also be differentiated by the derivative law of inner product. Summing them up, and we can obtain this equation. Continue from this expression. Erase 0. As a property, the transpose of the product of two matrices is equal to the product of their transposes in reverse order. To minimize the squared sum of errors, its derivative should equal 0. Move the first term to the left side. Simplify by dividing by 2. Let's continue from this equation. Take the transpose of both sides. Using the transpose matrix property, we can transform the left side in this way. Next, using the transpose matrix property, the right side is also transformed in this way. Since the product of matrices is subject to the associative law, for simplicity, let's combine transpose of x and original x and transform. Furthermore, let's transform the part inside the parenthesis in the right side, using the transpose matrix property. Let's continue from this equation. Let's focus on the underlined part on the right side. Let's combine this part together and consider the inverse of this part. Multiply both sides by this inverse matrix from the left. The underlined part of the right side will be identity matrix. Therefore, we can simplify this equation in this way. By swapping the left and the right sides, we can say that the formula is the regression coefficient vector that we saw previously. It shows that we can find a vector of regression coefficient using the dependent variable vector and transpose and inverse matrices of independent variables. Thus, in multiple regression analysis, the regression coefficients can be obtained by using the inverse and transpose matrices. Although calculus is outside the scope of this course, here I briefly explain the product rule for the derivative of the dot product of vectors. When two vectors ux and vx are functions of x, the derivative of their dot products with respect to x is found by this formula. That is, when differentiating the dot product, differentiate one vector and take the dot product with the other vector. This is done for each of the two vectors and then added together. Thank you for watching. Please thumbs up and subscribe to my channel.